the agenda I had was fairly comprehensive, and I'm not going to be able to cover everything in depth that I would have liked, but I think still the journey has been a good one in covering a whole range of topics. With that, if you continue to work on this, you should be able to open up books and papers and dig deeper as you need. But most important, my goal is when you use the software, you should be aware. You should have a sense of how it does it so that you can use it with intelligence. In fact, I'm thinking of constructing a course like this. But let's get back. So today and the next lecture, Wednesday, I want to focus on this so-called method of weighted residuals. Okay, it's another approach, and all these culminate in the best set of algorithms. The ideas distilled over 40, 50 years, and those are the ones that find place in COMSOL, in MATLAB, in open form, which is, in fact, there are a lot of open source software, but it's a bit more engaging to use them. That's another thing that is in my agenda, how to develop tutorials and stuff so that open source software becomes more easily adaptable for practical applications. So all these ideas have been distilled in these suite of software. But when they don't work, or the other important aspect which I wanted to cover, and I think I said in time permits we'll explore that, is the modeling itself. Okay, when you're dealing with complex systems, multi-phase systems, or it is reacting systems, or heat exchanging, mass exchanging systems, fluid mechanics is the underlying thing that carries all these processes, whether it is heat transfer, mass transfer, or reaction engineering. So it provides the framework for understanding all of transport phenomena. That's why I called it computational transport phenomena. But we have been focusing more on the computational part than on the transport part. Except transport, we use it only through a few examples, and the project that you're doing will all involve some element of transport phenomena. So the thing in the box is a thing that you should be able to engage in a discussion with me in your final oral exam. What is forward time central space, backward time central space, Craig-Nicholson, Richardson, Dufort-Frankel. There are a lot of finite difference methods that we saw for parabolic partial differential equations and for hyperbolic partial differential equations. We saw the Lax-Wendroff method. Okay. The idea is that you take the partial derivative and replace it by its finite difference approximations, throw in a good measure of ad hoc mixing of these approximations, like saying I'm going to take the average of the two different time levels, things like that. And when you do that, then you need to worry about consistency of the approximation. So given a finite difference approximation, you ask the reverse question. For what differential equation is this a consistent approximation? So we saw how to do that by basically going backwards, by using the so-called deriving the modified differential equation from the finite difference equation by using Taylor series. And that's an important concept. And we also saw what stability is, order of accuracy in the truncation error, stability, and what is convergence. Convergence meaning grid independence. As you refine the grid, the difference equation solution approaches that of the differential equation solution. All these ideas can be tested and explored only for linear problems. When you want nonlinear problem, we hope that the same method that we have developed here will be applicable without really a lot of proofs, but you can always do a grid independence test and see whether the results seem to converge. And we introduced the idea of a von Neumann stability analysis, which is very similar to the normal mode stability analysis used in fluid mechanics and other areas. Basically Fourier analysis based approach, where you derive an equation for the error from the finite difference equation by subtracting the finite difference equation with the exact solution. So the error equation has the same pattern as the finite difference equation. And then you decompose the error. An arbitrary error can be represented in terms of its Fourier modes. So you take one particular Fourier mode, sine omega m x, for example, one space dimension. And so omega m is your frequency that you can change. So span the entire frequency. In a sense, it is also the same idea that you use in Nyquist stability analysis and process control. Okay, so you do the stability scanning in the frequency space. Okay, so the same idea here, and you determine under what conditions the relation between the error at the current step and the error in the next step, that amplification factor is really not an amplification factor, it is less than 1 for stability. If it is greater than 1, it is unstable. That numerical method is unstable. So one of the things that you need to be able to differentiate or be aware of is when you're solving and when something blows up, like you get 10 to the 31 for drag, what is it causing it? Is the problem unstable or is the numerical method unstable? Okay, so you need to be able to sort that out. So you need to be able to do a series of tests, which are typically grid refinement tests, because the stability analysis tells you that the step size must be less than a certain number. Okay, the grid size or the time step size, or in partial differential equations, this courant number, which is a combination of u delta t over delta x, that must be less than 1 for certain algorithms. But that number may be 1, maybe 2, whatever, but there is a certain bound, mostly for explicit methods. But if you introduce implicitness in your algorithm, then they become less sensitive to your choices of grid from the stability point of view. Okay, and we saw how to extend these ideas to 2 spatial dimensions. There's really nothing challenging in there. All the ideas covered carry forward straightforwardly, but the bookkeeping gets horrendous. And that's where there is a lot of money to be made. If we can automate this bookkeeping process, and all these software simulators do that, so they can handle 3 dimensions and time effortlessly in any complex geometries. Now, finite difference method is only for well-structured geometries, or square, circle, etc. If you have a complicated shape, it's difficult to fit a finite difference grid in a complicated shape. And that leads to the finite element and the finite volume method. Next week we will see an introduction to those. But before we go there, the method of weighted residuals is an approach that will help us as an introduction to the finite element method. One idea that I did not talk about is an important one called the ADI method, alternating direction implicit method, that works only for these kinds of problems, okay, where you have 2 spatial dimensions. We saw the implicit method, for example, okay, and we saw the crank-Nicholson method, which is also an implicit method. So in alternating direction method, you have 2 directions, spatial directions, x and y, and time. Okay, so if you take a geometry like this with time and this as x and that as y, then you have a grid in space and time marching in time. So you make implicit in one direction and make it explicit in the other direction. Take the data from below. When you're approximating the derivatives from the y direction, you put them at n plus 1. The x direction, you put them at n. What advantage do you get? Because then you'll get only a tridiagonal system that you need to solve for each line. Okay? So you'll get a tridiagonal equation for each line. So you put a loop around that and you can sweep in one direction. But you cannot continue to do that as you march in time, because then the information has a bias. It always propagates in one direction. So the ADI method, again, it's an ad hoc suggestion. The ADI method says, going from n to n plus 1, make it implicit in y, explicit in x. Going from n plus 1 to n plus 2, make it implicit in x, explicit in y. Okay? So if you're curious, I think you should write down the equations. It's not very difficult to do, but it's going to take us half an hour to write down the equation and see how it looks. But it is an important idea that produces a very stable method and a very powerful method for 2-dimensional and 3-dimensional parabolic marching type of problems. Okay, so that's a kind of a review of what we have seen before. Now I want to start talking about revisiting the functional approximation ideas that we talked about. So all these material are taken from Wikipedia and other sources. There are lots of material on the internet. If you search for method of weighted residuals, so many math department people put their lecture notes. So I was getting out of time, so I just took all this material from there and cut and paste. What is important for us is to follow through the idea, the thread of ideas that evolve in generalizing what we have learned for vectors to functions. Okay, so we learned how to solve equations of this type, starting with this ax equal to b. Okay, that is a linear system of equations. And we saw direct methods, we saw iterative methods, etc. And we saw something called a spectral representation of the solution. Do you remember what that is? We treat A as an operator. We find out all its eigenvalues and eigenvectors, right? So those eigenvectors are a good basis set. Why? Because they are linearly independent. Okay. So we look at this vector x as some arbitrary vector in an n-dimensional space. And that arbitrary vector we said we can write as a linear combination of alpha I xi hat are the eigenvalues of this operator. And we're going to see a parallel in that when we go from algebraic equation to a differential equation, du equal to f of x. Okay, so u now is an unknown function. Instead of unknown vector x, u is an unknown function. D is a differential operator. So d could be something like d square dx square plus x times d dx, operating on something. That something is u. Okay, so you can see the similarity. So from A we can get the eigenvectors, and if A is symmetric, the eigenvectors are orthogonal. That is, every eigenvector is perpendicular to everything else, and they form a linearly independent set. And then I can construct this arbitrary vector x, the solution, in terms of a linear combination of those eigenvectors. And that is what we call the spectral representation. We will never do that. It's not efficient. Why is it not efficient? Because it is a lot of effort to calculate all the eigenvalues and eigenvectors, particularly if A is very large. Okay, if you have 10,000 equations, that's a huge task to do that. So LU decomposition is the most efficient direct method, and we have iterative methods that are efficient based on Gauss-Seidel, conjugate gradient, GMRES, and things like that. They're all available in COMSOL, in Fluent, etc. So one of the things that we talked about when we talked about the orthogonality is how do we test whether two vectors are orthogonal? We just take those two vectors A and B and define an inner product between them. So these are the inputs, A and B, two vectors, and we define a dot product as A dot B. And if A dot B is 0, that tells us that they are perpendicular to each other. Okay, so that is a test that we can use. If you give me any two vectors, if I have to find out whether they are orthogonal, I use this definition of a dot product to see whether they are orthogonal. So I need to come up with an idea for functions, because what I want to do is I want to take this arbitrary function and write it as a linear combination of some set of basis functions, phi I. I should know what those basis functions are. Okay, and it turns out that in that particular case, I don't follow the route because calculating the eigenvectors is a lot of effort. In this case, I'm going to propose the basis functions. It can be solutions to the differential equations. Then we would call them eigenfunctions. But it need not be. It can be just polynomial approximation. It can be orthogonal set of polynomials, orthogonal functions. So we need to introduce the notion of what is orthogonality for functions. Okay. So how would we do that? So that's how we do that. So we take two functions, f and g, okay, and we define an inner product and indicate it in this way, typically f comma g within parentheses. That is defined as the inner product between these two functions. But what is the definition of that inner product? It is essentially product of f and g, because they are functions, they are integrated over that space between the limits a to b with respect to a weighting function. So we also introduce a weighting function. Okay, that's how we define an inner product between two functions. Now if that inner product is equal to 0, then we say that the functions f and g are orthogonal. They are perpendicular to each other. Okay, is that clear? Any questions on that? Yeah?
How do you, I guess we're going to get, how do you use the weighting function?
How do you?
Determine or define the weighting function.
The definition is arbitrary, right? So this is how I define what an inner product is. So you can define an inner product with respect to any weighting function. Then you will say that those functions f and g are orthogonal with respect to that weight function over that interval from A to B. Okay? It depends on, often it suggests itself, but we will see that we are free to choose this weighting function. Okay? But the first thing is that you should be able to relate what we saw in the vector space and move that to function space. The idea that we can define an inner product between two vectors. We can also define, in fact, you can go back and generalize that inner product definition of vectors by putting a weighting factor there too. Right? So, and the book by Ramakrishna on linear operator methods in chemical engineering is he's a chemical engineer, but it's a very highly mathematical book. And it takes the functional analysis approach to define these things in a very formal way. But using examples from chemical engineering, they illustrate a lot of these ideas. Okay? So that's a key step that we need to subscribe to, that there is a definition of an inner product that I can use to check this notion of whether two given functions are orthogonal. Now you can ask the question, why is it important? Okay? How did we use that idea of orthogonality in the solving the linear systems? Yeah, if they are orthogonal, they are linearly independent. So it allows you to construct an arbitrary vector in terms of that basis vector. It provides a good basis. But what is the utility of it? That is, in here, as I said, it's a concept, it's very nice, but we don't do it because it involves a lot of computations. Okay? But it allows you to select one vector from the summation of all vectors. If you remember, when you're implementing initial conditions and stuff, you can, in fact, to find this coefficient, there are n coefficients here, right? So if you give me arbitrary vector, my job of finding a spectral representation is to find what alpha is. I know the eigenvectors because you give me the operator A, I know all the eigenvectors are. Then you give me an arbitrary vector and say represent this vector in that space using this xi bar as the basis. That essentially means I need to find the value of alpha I, right? Because I know x, I know this, I need to find alpha I. How do I do that? I go and take the inner product of this with respect to xk, for example, xk with x, inner product of that. On the right hand side, xk with xi will be equal to 0. It's a summation. Only when k equal to I will get a non-zero term on the right hand side. So I can immediately write, in this case, alpha k as simply the inner product of xk dotted with x divided by xk dotted with xk. So it allows you to select one component because they're all independent of each other. If I take the product, I mean, if you give me this and you give me this and you ask the question, what is this? The answer is given here. How did I get that? I simply take the dot product of xk on both sides. Okay, xk. But when I expand in the summation series, unless when k equal to I, everything else is going to be 0. Okay, so I pick only that particular component alpha k, and that's what allows me to construct those coefficients. Wouldn't it be nice if I can do the same thing with functions? Okay, where did I have the function? Here. If you give me a known function u and say find a spectral representation of that, the same problem, I need to find alpha I. So if you give me u, and if I have this notion of orthogonality, then I will take phi j, take the inner product with that, and what will I get on the right hand side? Okay, and here I'm saying you give me a function and you give me the basis functions, and you ask me to construct that arbitrary known function in terms of the basis functions. Same problem there, arbitrary known vector in terms of the basis vectors. So we did use the orthogonality property to extract what is each one of those coefficients. So here k is going to go from 1 all the way to n. Okay, the same idea here. So I'm taking the dot product of the entire equation with respect to phi j. So phi j u, because u is known, phi j is known, and you have a definition for an inner product, we can calculate that. It's going to be a number. Okay? And on the right hand side, what will I get? That's what I'm asking you. coefficient. Okay, so you have a summation, right? So you will have the summation of alpha I, and then you are multiplying everything by phi j. But phi I is already there, right? And that is the inner product. Okay, but what is phi j times phi I if they are all orthogonal? Only when j equal to I it is non-zero. Everything else will be zero. So from this summation, all you will get is alpha j. There is a delay, right? Alpha j times the inner product of phi j with respect to phi j itself. And if they are orthonormal, what does that mean? That inner product is 1. Okay? So you can select all these, you apply this for j equal to 1 to n. So you get all the coefficients, right? So the idea that we have learned in vector spaces can be translated into function spaces and then adapted to solve differential equations. So in that particular case, u is not a known function. If you are given a known function and say, do a polynomial curve fitting, you take phi i's basis set as 1, x, x squared, x cubed, etc., right? And then you do the polynomial curve fitting. If the functions are orthogonal, you don't have to solve a set of linear algebraic equations. Remember, when we did the curve fitting, we said that if you write this in terms of simply alpha I x to the power I minus 1, that's one basis set. Okay, that is 1 x, x squared, x cubed, etc. But that set is not orthogonal. Okay, 1 x, x squared, x cubed. That basis set is linearly independent, but it's not orthogonal. So if you try to solve this, what do? Well, you evaluate this function at n locations or n plus 1 locations. Then you evaluate that at n plus 1 locations. That is the least squares curve fitting or polynomial curve fitting. Okay, so you end up with a matrix system that we saw when we actually looked at the functional approximation before we did the Newton method. Okay, but if the functions have this orthogonality property, then it is like diagonalizing the matrix. It's another way of looking at it. Okay, so you don't have to solve, they are not coupled, they're all uncoupled. Each coefficient can be found out from one equation like that. Are there any questions in that? Am I making sense or not? Yeah? Kind of skeptical.
Do you want to check the PI once? Do you want to check the PI?
Thank you. Yeah. Are you guys hearing us today? Okay, thank you. All right, thank you. Do you guys have any questions? I'm just trying to set up the stage for method of weighted residuals. Okay? All right, good.
What's happening?
In the initial 10 minutes, it seems to work well, the screen. After that, okay, so these are just the material taken from that internet source. It essentially says that this is the definition. Oops. Okay, so the inner product of the function with itself is what we would call the norm. Okay, and if you are given a sequence of functions, you see here, they are orthogonal if this condition is satisfied, that inner product between two different functions, m and n, is always equal to 0, but m is not equal to n. And that is a very important property. Okay? And if two functions are orthogonal, then it is essentially the norm multiplied by the Kronecker delta, mn. So when is it m equal to n, delta is 1, and when m is not equal to n, it is 0. Okay? You can normalize that and then you will get the so-called orthonormal functions, and that's what is indicated here. Now the question is, if you give me a set of functions 1, x, x squared, x cubed, etc., and suppose they are linearly independent. Okay. So can I, but they are not orthogonal to each other. Can I construct a set of orthogonal functions? What is this question similar to from what you have seen before? And what is the method that we have seen that will work? You are not a student in this class, right? I want others, this is a question that you're going to have in an exam. What is the method that we saw? Gram-Schmidt procedure, right? So essentially, if you're given two, if you're given two vectors, we saw how we can develop a set of orthonormal vectors from that, and that is Gram-Schmidt procedure. So if this is x1 and that is x2, we will normalize this and call it as v1, and then we will write v2 as equal to x2 minus the component in the x1 direction. That is, we take some vector arbitrarily. We're going to make every other vector perpendicular to that. That's what Gram-Schmidt does. I want to review that because I'm going to apply the same idea to functions. If you give me a set of functions that are linearly independent, how do I generate an orthonormal basis set? Okay? There are two ways of generating. One is exactly the Gram-Schmidt procedure that we saw. The other one is as solutions to differential equations. The Fourier series, for example, the Bessel functions, the Legendre functions, they are all orthogonal functions, but they come as solutions to some sort of a differential operator, differential equation. The Sturm level theory gives us a whole lot of these orthogonal functions, and there is a book this thick on orthogonal functions, okay, and all their properties, recursive relations to see how we can construct higher order functions from a lower order functions using recursive relationships. But the basic idea, one idea is essentially take the first vector and from the second vector subtract the first vector. So we introduce a coefficient, we'll call it say C naught multiplied by V1. So V2 is x2 minus C naught times V1. That is, I need to find that amount of C naught that will exactly cancel the components in V1. So in a sense, what I'm saying is I'm going to decompose x2 into two directions. One is in this direction, the other one is in that direction. And I'm going to subtract the amount that is in the x1 direction. Then I will get a component in the x2 direction. So I need to find out what that extent is. So I need to find out what that coefficient C naught is. So how did we do that? We impose the condition that they should be perpendicular, right? So we take V1 with respect to V2, that is the inner product of V1 dot V2 on the left-hand side, okay? And that should be equal to the same thing, V1 dot x2 minus C naught times V1 dot V1. But what is V1 dot V1? Is 1, because we have orthonormalized it, right? We have normalized that vector. Now V1 dot V2 should be what? 0. We want it to be equal to 0. So we set that equal to 0. Okay? Then you can solve for the only unknown C naught. Because we know V1 from the previous step, we know x2, which is the next set in the vector, and we know V1 and V1. So C naught is equal to this. So we found out to how much of V1 should we subtract from x2 so that I get V2. Now you normalize V2. And then go on. You take the next vector x3 and from that subtract V1 and V2. Okay, so you'll have two conditions. But those conditions will be V3 must be perpendicular to V1. That's one condition. V3 must be perpendicular to V2. That's the next condition. So we repeat that process, right? So we can construct an orthonormal set of vectors from a given set of independent vectors, linearly independent vectors. I guess that's probably coming down a little later because I started talking about it a little sooner. This is an example of an orthogonal set of functions. The functions here are sine n pi x over L. N is equal to 1, 2, 3, etc. So there is an infinite set of functions, and they are linearly independent. They are perpendicular to each other. How do we test that they are perpendicular to each other? Well, we take sine m pi x over L, and take the inner product with sine n by x over L. Okay? So you need to carry out this integration. It's back to normal. And you will find when you carry out the integration, of course this is not going to be equal to 0, but this is when m is not equal to n, what happens? M minus n is going to be an integer number, and the limits are x0 to L. So when you put L, you're going to get sine pi, sine m minus n pi. So they're all going to be 0. Okay, and I guess, yeah, the same reason, this one also, even though m and m may not cancel, but you'll have sine m plus n pi. And because m and n are all integers, they will all be 0. Okay, but when m is equal to n, that's when we need to worry about. The integral is the same, whether m and n are not equal or equal. So when m is equal to n, what happens? Then this should not be 0, right? Which term is not 0 there? The second term would still be 0, m plus n, right? But the first term, m is equal to n, so you'll get 0 in the numerator, but you'll also get 0 in the denominator. So it is determined, the limit is determined by the L'Hopital's rule, and it turns out that if you can do that, you'll find that it is not equal to 0. Okay? And that's how, for any function, this is how you would prove that they are orthogonal. Or if they are not orthogonal, you'll use the Gram-Schmidt procedure with the same scheme to evaluate what these coefficients are. You'll subtract one function from the other function. Okay? So Fourier series then is an orthogonal basis set, and that comes, in fact, we've seen in the transport phenomena course, when you have separation of variables in a diffusion equation, your solution is written in a planar geometry. It's written in terms of sines and cosines. That occurs naturally. Okay. There are numerous other sets of functions that are orthogonal. Okay. As I said, the Handbook of Mathematical Functions by Abramovich and Stegen, I think, has a lot of these functions and their properties and their tables. It was produced, I guess, before the days of computers. So to calculate these functions, you'll actually have tables of numbers of these functions at various x locations, independent variable locations. So where do these orthogonal functions come from? As I already indicated, there are two sources. One is, if you're given a linearly independent set of functions, you orthogonalize it using the Gram-Schmidt procedure. So this basically reviews that idea. The other one is, it is coming from differential equations, solutions of differential equations that give rise to a whole range of functions. So the idea of linear independence, how do we test linear independence with vectors? Do you remember? If you give me a set of vectors, I construct, think of each f1 being a vector. Okay? Then I will write it as a linear combination of c1 x1 plus c2 x2, etc. And I will construct the matrix, right? And the matrix would be, that is, I write summation of ci xi equal to 0. That's a vector, that's a vector. So ci are the constants. And if they are linearly independent, the only solution that ci's can have is 0. Okay? So you verify that by rewriting that as a big matrix X multiplied by C, the vector C. So there's no I there. This is my, it's not a smart board. This is not changing. Okay. So it should be just C. Okay. X times C equal to 0. So what is the property on X? Its determinant should be non-zero. If it is 0, then C could be anything that you want, right? The determinant of X should be non-zero. That means that forces C to be equal to 0. And we need to have a very similar set of tests to see whether a set of functions is orthogonal. And you follow exactly the same idea, but you will have to take, you need to construct that n equations. Okay? So this is the function, and we need to set this, for example, is equal to 0, and show that the only way that you can satisfy is when all the C1, C2, C3 are all 0. So you take that function and take its derivative with respect to x, first derivative, second derivative, etc., and organize them as a matrix. Okay? So you'll have f1, f2, all the way to fn, In the second row, you will have f1 prime, f2 prime, fn prime, and continue on. So in the very last row, you will have the n minus 1 derivative of all these functions. That multiplied by these coefficients c1, c2, c3, cn is equal to 0. So what would be the condition? This matrix is called the Wronskian. Okay. So, so you know all the functions and you are testing whether those functions are linearly independent. So to test, you construct this matrix containing all the derivatives and check whether its determinant is non-zero over the entire interval of a to b for every value of x. Okay? Then you will know that that set of functions is linearly independent over that range. So he is giving you an alternate way of testing it. Can you make sense out of it? This equation 2,9, what is he trying to do? Taking the inner product from that equation with respect to fk. Okay? So you have the function f1, f2 all the way to fn. You take the inner product of that function with respect to fk. So if they are orthogonal, what should happen? All of them should be 0 except for this one. Okay? And that way you will show, because this is then the norm of the function k, that cannot be 0, right? So ck must be equal to 0. Now k is general, so you can set k equal to 1, then k equal to 2, then k equal to 3, and that way you show that all of the k values, c values are equal to 0. That's another way of testing it, but you need to have a routine or a function that will calculate the inner product in return. And then you can apply this test. So let's look at how do we construct this orthogonal set of functions using the idea that we saw in the Gram-Schmidt procedure. So if you're given a set of functions that are linearly independent. Okay, so f of x is fn of x is a linearly independent set of functions, but they are not orthogonal. Okay, so I'm going to take the first function and normalize it, if you like, and call it as g0. So the set g is going to be an orthonormal set of functions. The f is the linearly independent set of functions that are not necessarily orthogonal to each other. So it's exactly the same idea. So the next function is going to be g1, which is f1 subtracted from g0. Okay, so the idea is borrowed exactly from finite dimensional vector spaces and applied to functions. Now in here, what is the unknown? C01, the coefficient C01 is the unknown. Okay, G0 is known in the previous step. Okay, and F1 is given in this set. So we want to find out G1 such that G1 is orthogonal to F1. Same thing, if you want to construct G2, okay, you take F2 and from that subtract the two previous functions. Okay, so that is G0 and G1. So now I have two unknowns, but I have two conditions. What are those two conditions? That G2 must be perpendicular to G0 and G2 must be perpendicular to G1. Okay, so using those two conditions, I can find out what those two coefficients are. Then he generalizes that idea. Okay, and if you take the basis function 1x, x squared, x cubed, it's a good exercise for you to play with. If you have some extra time, I know you don't have right now. I hope the learning doesn't stop after this course. Maybe after the course is over, get back and work with that. Okay, so f of n equals x to the power n. That's my basis set. That's linearly independent. I can test that by putting on the previous test that we constructed, right? So n equal to 0, 1, 2, etc. So essentially follow the same procedure, and what you will get is a set of functions that are called Legendre functions, polynomials, that are. He works out the math, but I just give you the final form. Here it is. Okay, these are the functions. P0 of x is 1, P1 of x is x, P2 of x is 1/2 3x squared minus 1. Every polynomial is a next higher degree, successively higher degrees. And I said there are two ways of generating that. One is through the Gram-Schmidt procedure, another one is through this. This is called a generating function. It has something to do with Sturm Liouville theory and solving differential equations. So we just pick the order and it directly gives you how to construct that polynomial of particular order. There are also something called recursive relationships, which would be P2 will be given as a linear combination of P0 and P1. P3 will be given as a linear combination of P1 and P2, etc. So there are several ways of constructing these polynomials and testing that they are indeed orthogonal. And in this source, I also found a nice picture of how those functions look like. Why are these functions good functions for solving a certain class of problems? Okay, so here, what is P0? That's P0, the first one. Which one is P1? The linear one, right? And P2 is the quadratic. Which one is P3? -1 goes up and goes back up there, right? It's a cubic, so it must have 3 roots. And these are what we call the roots of orthogonal polynomials, and they have an important role to play in giving us tremendous improvement in accuracy. So orthogonal collocation comes from this. So you construct your polynomials and then collocate at those roots. And we'll talk about what collocation is very soon. Okay, so that's going to be P3, and this is going to be P4. They're all nicely scaled between minus and plus 1. Okay, that's one of the reasons why these polynomials are well behaved. They are all orthonormal polynomials. So the idea is that if you give me any arbitrary function f of x, I can approximate it. By a polynomial of a certain degree, where I write the polynomial as a linear combination of not just 1x, x squared, x cubed, etc., but some function phi, which is an orthonormal basis set. In this particular case, phi could be p. But phi could be sine and cosine in Fourier series. Phi could be J0, J1, etc. Bessel functions. Did you have a question?
Well, why is it if we're taking the functions and making them kind of orthonormal, breaking it down, why is p of x only an approximation of x?
Good question. Why is this polynomial an approximation to f of x? Because f of x is a very general function. If I tell you that f of x is equal to this polynomial, and I say, okay, I'm going to write that f of x in that polynomial, and then I ask you, what will be the coefficient for a0, a1, a2, and a3? These coefficients will all be 0, that coefficient will be 1, because that polynomial is exactly that function. So if I give you that function as one of these functions, then I'm picking the coefficient. So what I'm trying to do in this is give the new function that I have proposed, f of x versus x, use this function. That's an error function. And I say construct the error function in terms of these polynomials. There's no way I can do that. These are all, polynomials are a finite number of terms, right? And this is an infinite series. So I always have to approximate it. Okay, so I'm taking the infinite series and truncating it. Okay, and that's, so unless the given function is a simple polynomial, okay, and if it is exactly the same polynomial I give you here, then the coefficients a would be simply zeros and ones.
So then would f of x be exactly equal to, could you generate an infinite series representation?
For what?
For f of x.
Well, yeah, it could be. It depends on what f of x. It depends on what f of x is. Here I give you f of x as this error function. In another example, I might give you f of x as pure sine function. Sine x. Try to construct an approximation for sine x with that polynomial, right? It's not possible because sin x is also an infinite series, right? So you will need to truncate that, and that's how you will get an error. And that's why this p is only an approximation to f of x if f of x is any arbitrary function. But if a special case where f of x is one of these, then you can make it exact. And you can make the problem extremely simple because one coefficient is going to be 1, all the other coefficients is going to be 0. Okay? But I can take a problem where the function is a combination of P3 and P4. I add them up. 50% of P3 and 50% of P4, I can construct a new function, right? And then I say, okay, go and find out what are those and I give you the function as a black box. I don't tell you where it comes from, okay? And then say, go and find out those coefficients. What you will find is one of the coefficients is 0.5, the other coefficient is 0.5, everything else is 0, right? So this allows you to construct the weighting factors backwards. Given an arbitrary function, how do I find the weighting factors using this as the basis set? But that need not always be an exact representation. And the problem gets even more difficult if this function is an unknown function, which is a solution to a differential equation. And that's where we are going. Okay? Once we understand this concept, then we are going to say, okay, now this f of x is a solution to a differential equation. I don't know what that solution is, but I can represent that solution in this form and take this and plug it into the differential equation and go through something equal to discretization, converting a differential equation into an algebraic equation through this method of weighted residuals, collocation methods, etc. Okay? It's a good question. That thought process is what I think allows you to digest the material a little bit more. So here we are introducing for the first time the notion of, not the first time, I think we did it in the linear algebra part, least squares, curve fitting, etc. But here f of x is a continuous function. It is being replaced by the polynomial, and so I'm defining a residual. The residual is the error between the known function and its representation that I'm going to construct. And in here, phi I are the basis functions. They are all known. Okay, so the unknowns are ak. So my question is, what is the best value of ak such that this difference is as small as possible? And that difference is what I call a residual. Now it gets the name method of weighted residual because I put a weighting factor there, and I choose that weighting factor. Okay, the different choices for the weighting factors gives rise to different classes of approximations: collocation method, subdomain method, orthogonal collocation method, etc. So those are all determined by what weighting factor that you choose. The basic idea in method of weighted residuals is you form the residual and weight it with an appropriate function, and then either set it equal to 0 or minimize it. Okay? So when you are minimizing it, the unknown, remember, is ai or ak. Okay? So you're taking the derivative of this with respect to the unknown coefficients a, which we did for least squares curve fitting when you have a data set, a given set of data points f, and you had the function to represent that. We did exactly the same for least squares. So the same idea. So when you take the derivative, you have squared, so that becomes 2, and then w of x, f of x minus this, and then the derivative, you have to apply the chain rule, right? You're taking the derivative with respect to ai. So this doesn't depend on ai, but this does. So of all the n terms, you take the derivative with each one of the ai. Of course, a1 with respect to a2 is what? 0, because a1, a2 are all independent set of numbers, right? They are not functions. So only when you take the derivative of this with respect to k, you will get a non-zero term 1. And that's what gives here. Okay, so I'm taking the derivative with respect to ai. When I is equal to k from the summation series, there are two parts. The first part is the chain rule. That is derivative. What is the derivative of the whole thing with respect to a? This whole thing with respect to a. That is twice that function multiplied by wherever the a depends inside that. I need to take the derivative, and that gives rise to phi ix. Make sense? Yeah? Question?
Why, so when you take the derivative ak with respect to, I guess, ak and s, why isn't it negative like this? Isn't the sign before the summation is the minus sign?
Because this is how I do, this is my definition of the given function minus the fitted function.
I understand, I guess, when
Yeah,
So
that's exactly what happens here. Oh.
why isn't the whole thing negative?
Okay. You are absolutely right. I'm missing a negative there.
Okay.
Thank you. The reason it didn't matter is this is set equal to 0. Right? So that is set equal to 0.
Make sure that I wasn't missing.
But you are right. When I take the derivative, I should get a minus phi I.
Okay.
Okay. If the basis set is, what is this? What have I done here? I formulated the residual, okay, and I have constructed the minimization condition. This is going to be true for every value of I going from 1 to n. Okay, so if I started with n sized basis function, then I have n equations. I have n unknowns in a case, so I need n equations, and this gives me the n equations. Now what I need to do is I need to integrate on the left side wx times f of x. I can do that. Wx is something I choose, f of x is given to me. On the other side, I will have to integrate ak times phi I phi k. If these two are known functions, then I can carry out the integration, right? And what I will get is from each I will get one equation that couples all the ai values. It's a linear set of equations that I can solve. Okay, so I converted the problem of approximating a function to a problem of finding a set of solving a set of linear algebraic equations. But the beauty is, if phi k and phi I form an orthogonal set, then from this summation, what happens? Only when I is equal to k, I will get a non-zero integral. Remember, the integral is integral of a to b w of x multiplied by summation ak phi k phi I. Right? So only when I is equal to k, I will get a non-zero. So it's an uncoupled set of equations. So from each equation, I can get one coefficient if they are orthogonal. Okay? That's where this property of orthogonality comes in very handy. You don't have to solve a certain system of algebraic equations. Is that clear? Any question? So, for the various subclassifications of these methods. So the problem now is we need to find these coefficients. Okay? And we have an equation. We have n equations to be able to find those coefficients, ak, a1 all the way up to an. Okay? So various choices that we make for the wx gives rise to various methods. Yeah?
I'm sorry, I'm going to backtrack here.
Yeah.
Why do we take the derivative and set that equals?
Because we want to minimize the error. The residual is the error between the given function f of x, okay, and its approximate representations with a basis set. So this difference is the error. If this difference goes to 0, I have a perfect fit. Okay. So this is the residual, and I want to minimize the residual. So minimizing the residual sets the derivative of the. So you're looking for the minima of function. Right. Yeah. So yeah. So the first method is called the subdomain method. So what is the idea here? You just pick wk of x to be equal to 1 in some subpart. Now for a one-dimensional problem, this is a sketch for, say, 2D. The same ideas would apply for 2D and 3D, meaning partial differential equations also. But in the one-dimensional case, if I have x going from A to B, okay, I'm going to divide this into various subdomains. Okay? And within each subdomain, okay, when k equal to 1, I'm going to set the weighting function here as 1. Everywhere else as 0. When k is equal to 2, I'm going to set the weighting function here as 1, and everywhere else as 0. So from each k value, I will get one algebraic equation. Okay? And so I will assemble n equations. I have n unknowns I need to find, and if they are orthogonal, what I said earlier works. I don't even need to do any of those. But if the functions are not, then you just divide your domain into several subdomains. That is the genesis of finite element method idea. There's one important difference. The difference is the functions that I have written, phi1, phi2, or p1, p2, the polynomials, are global functions. They are functions that span the entire domain from A to B. In finite element, what we will do is follow a very similar idea, but our functions will be defined only within each domain. Outside of the domain, the function will be 0. Here, we are making the weighting function outside 0. Okay? And there is an important difference. So when you look at the structure of the matrix, once you go through this process, you will find that these matrices that depend on what we call global support, the function phi spanning x in A to B, will always have a dense matrix, full matrix. So in collocation method, what we do is we choose the weighting function to be a delta function. What does this mean when I write it as a delta function x minus xk? When x equal to xk, it is 1. Everywhere else it is 0. Okay? You know the Kronecker delta in terms of discrete I and j. Okay? But this is a continuous version where this function is equal to 1 when x equal to xk. So that is a point. So previously we said we want to impose that condition over each subdomain. Now we are saying I want to impose that condition at selected points. And that's why it's called collocation method. If I choose those points equally spaced, I get the equally spaced collocation point. And if I choose them to be roots of the orthogonal polynomials, then I get orthogonal collocation. Okay? That's the only difference. And orthogonal collocation seems to converge much, much faster to the real solution than the normal collocation. Then we have the least squares method. And they are all in the same framework. All we are doing is we are free to choose the weighting function, and we're choosing the weighting function to be different. So in the least squares method, the weighting function is said to be equal to dr dak, the residual, the derivative of the residual with respect to ak. And the purpose in each case is to generate n equations, because we have n unknowns, okay, in each case. And the interpretation here is that you are minimizing the integral of r squared dx. This is exactly what we did. So when you take the derivative to 2r dr dak, okay, and that's why you interpret the weighting function to be equal to the derivative of the function itself. If you go back, you will see So this is the function. So if I pick the weighting function to be equal to the derivative of r with respect to ai, then it is minimizing this integral, the square of this integral, r squared. Okay. And there is an example with numbers that implements each one of these methods. Okay. And in the Galerkin method, that turns out to be one of the powerful methods produced by a Russian mathematician. The choice is the weighting function is the basis function itself. We use the weighting function as the basis function. And then there is another method called the method of moments, where you pick the weighting function to be equal to x to the power k minus 1. So these are considered as moments of the various functions f. Okay? So the whole class of method of weighted residuals essentially gave rise to a number of different methods. Of these, we know that this is probably one of the most powerful methods. There's a lot of theoretical analysis later on saying why this should be, but we are going to see it only how to implement and what do we get. So we start with our famous test problem, dy dx minus y equal to 0 over the interval x 0 to 1 with an initial condition y of 0 equal to 1. We know the solution to this. The solution is, analytical solution is y is equal to e to the power x, okay, in that interval 0 to 1. It's a first order equation. So we want to go through the process of how do I construct the residual, how do I construct the matrix, how do I choose various weighting functions. I'm going to go over this in detail for the first case and then give you the result for all the other cases. Remember, the equation from the other part is this: dy dx minus y is equal to 0 with an initial condition that y of 0 is equal to 1. Okay, I think I probably put tilde there. So we are going to construct a solution, propose a solution of this form. And what we would like is for the basis functions phi j to satisfy the homogeneous boundary condition on the problem. Okay, so I split this into two parts. Y0, which is designed to take care of boundary conditions explicitly, so that phi j, when you evaluate phi j on the boundary, simply equal to 0. That's a proposal. Okay, that's a proposed solution form. Obviously, it's not going to satisfy the differential equation. If it does, we have found the analytical solution. But in this case, we know it won't satisfy because it's a finite number of terms, and e to the power x is an infinite series already. Right? E to the power x is the solution to that particular problem. So y0 I fixed to be equal to 1 because I want this to be the boundary condition. And I'm picking my polynomial to be simply x to the power j. So they are not orthogonal to begin with. Okay? If it is orthogonal, the problem becomes easier. Okay? But in this case, it is not orthogonal. So I have introduced n unknowns, and these unknowns are these coefficients that I need to find out. Okay? So I first formulate the residual. What is the residual? The residual is a function of these unknowns, which I need to solve. But it is also a function of x, which I can integrate. I know. Okay? So what have I done here? I've taken this definition and plugged it into these two locations to form the residual. So left-hand side minus right-hand side of the differential equation is defined as your residual. So you see here, that is the definition for the proposed solution. Okay, and this proposed solution, the proposed function appears twice, and in each case we replace it with that particular function. And so A appears in two locations. If the differential equation is more complicated, the algebra gets more complicated, but the idea is the same. Propose a solution, take that solution, make sure that it satisfies the boundary conditions. If not, then you will have boundary collocation. You will have extra unknowns. Okay? But in those cases where you can make it satisfy the boundary conditions, and then you will end up with only n coefficients as unknowns. And you need to generate n equations where this residual will be 0 in some sense. So it could be collocation, which says the residual is exactly 0 at selected points, nowhere else. You can use the subdomain method, where the residual is 0 in each of the n domains that you divide your domain into. Okay? So when you take the derivative of 1 with respect to x, it will be 0. And when you take the derivative of the summation will remain, but you will get aj. Derivative is with respect to sorry, we are doing the derivative here on the differential equation. I lost my train of thought for a moment. I thought I was taking the derivative with respect to a. We are not minimizing yet. We are just finding what the residual is. So we are plugging this expression into the differential equation. So I am taking the derivative with respect to x. Okay. So I will get j times x to the power j minus 1 from this term when I take the derivative. And the next term will remain as it is, x to the power j, which remains as such. And both of them have aj, so I've taken aj as a common factor. Okay, so the minus 1 here comes from the second part. The first part goes to 0 when you take the derivative. Yeah?
Maybe I missed this. We're setting up a residual, like if you propose a solution, and then we're plugging it back into the original form of the differential equation. The residual, as the residual, the way, and that's how we define the residual. Is there a reason we didn't define it like the way it was defined before, the weighting factor and the integral with the weighting factor and the difference? We just went over it.
No, this is just the residual. Okay, and then you're going to make the weighted residual as equal to 0. What we are doing, what we are calculating here is just the residual. So if you go back, oh, I guess there is a, yeah. This is the residual that I should have called this as the R. Okay, and this is then the weighted residual. Okay. And I'm minimizing the weighted residual. Okay. So what I'm constructing there is just this highlighted part. That's a good point. Okay. Yep. The residual is simply the left-hand side minus right-hand side of a given function, because they are not exactly equal. Okay? So in this particular case, the difference between these two is the residual. Okay? And I'm squaring the residual, weighting it, and then I'm finding, I guess I should call this the objective function, which is the sum of the squares or the weighted square. Okay? And I'm minimizing that objective function, which is related to the residual. The residual is simply the difference between the left side and the right side. So you see the next step, right? So this is what I call residual. So there is a problem in the nomenclature. I called R something else there. I should have consistently called R as the residual, and here is the weighting factor. So it is this one that I want to set equal to 0. The weighted residual integral of that in the limit that I'm interested in. In this problem it's 0 to 1. Okay? So I've just illustrated in detail one method, the Galerkin method. It's going to take a lot of time to do each one. So I would encourage you to kind of fill in. So I've given you some of the tables, but it's probably worth filling in at least one table.
One more question. The weighted residual function, again, before we had set the derivative with each respective coefficient equal to 0. Here we're just setting the straight weighted to 0.
Right. So that's one way of finding the coefficients.
So
that is the least squares method. If I take the derivative equal to 0 and then solve for these, I get the least squares method. Okay? That's why I said in the least squares method, if you remember, I think there is a nomenclature problem I introduced that probably confused you. The least squares method, I said, this is the derivative of the residual itself. Okay, so when I call this with R, that's probably not the right nomenclature to use. Okay, that's an objective function that I want to minimize, and in the least squares method, I take the derivative of the objective function to set it equal to 0. That makes the weighting function as equal to what I should have called as R, which is just this part. Okay, this is the residual, and taking the that derivative of the residual with respect to A equal to 0, that becomes the weight function for the least squares method. Okay. So right now we are doing the Galerkin method, and in the Galerkin method, the weighting function is the basis function itself. Okay, so you put the basis function here as the weighting function, and R you substitute from whatever you had here. Okay, this entire expression, and carry out the integral. So this problem is tedious to do by hand because you need to evaluate a lot of these integrals. Does COMSOL do all these things? The answer is it does it internally for you in a finite element context where the bases have local support in each element, not the entire global support. Here all these basis functions are introduced in the entire interval 0 to 1. So you need to calculate these integrals over the entire range 0 to 1. So you substitute that in, and for k equal to 1, 2, and 3, these are the three choices for the weight function. You carry out the integration in detail. Okay. And what do you get out of this? You get an algebraic equation. So you have converted the given differential equation into an algebraic equation for k equal to 1. Okay, you need to carry out this entire integration and substitute the limit. So x will disappear once you do the integration. The only unknowns here would be a1, a2, and a3. So you get your first linear equation. Why is it a linear equation? Because we started off with a linear differential equation. If you had a nonlinear differential equation, what would you end up with? If you had a nonlinear differential equation, instead of the original one, I had given dy dx minus y squared equal to 0. How would this change? We would still formulate this residual in the same way. Wherever you had y, you're going to replace it by the proposed solution. So you will have a y squared. What does that do to the coefficients? A1, A2, A3. They will all have squares in them, right? So that becomes a nonlinear algebraic equation. So if you have a nonlinear differential equation, you end up with a nonlinear algebraic equation. And a linear differential equation, you end up with a linear algebraic equation. It's a discretization process. You can see in finite difference, that was a piece of cake. You just write down the approximate differences and it's easy. But here, you need to go through a lot of intermediate gymnastics to carry out the integration, substitute the limits to find out these coefficients, 1 over 2, 2 over 3, 3 over 4, etc. Okay? And then pick k equal to 2, okay, which is your next basis set. So that is x, and k equal to 3, that is x squared. The r remains the same, and you carry out the integration in detail. But these are all quadratures. It's fairly easy to, you need to know how to integrate x to the power n. Okay, then you can find out. So you get the second equation and you get the third equation. So 3 equations and 3 unknowns. Put them in a vector matrix form and you get a system of linear equations. Okay? So all these coefficients have come from integrating the basis functions, but they are not orthogonal. If the functions were orthogonal, how would this matrix look like? Diagonal. If it was orthogonal, then all the derivatives of phi I with respect to phi j will be 0. Okay? So it will only be diagonal. But because it is not orthogonal, you end up with a full matrix. Okay? And from each one of these equations, you need to separate the b. So where does the b come from? In finite difference method, the b came essentially from boundary values. But here, let's look at the first term. Where does the b come from? Anything that doesn't have the coefficient, so the first term. Right? Anything that has the coefficient like a1, a2, a3 remain on the left hand side, but the integral of minus 1 dx. Okay? In the second case, my integral of minus x dx, minus x squared dx. Each one will give rise to one of those b terms on the right hand side. And you invert that and you get these 3 coefficients. So what have we done? What have we achieved? We have constructed an approximate solution. So you can take these a values and put them back in this equation. So you have an analytical representation of your solution which satisfies the differential equation in your approximate sense. Okay? By minimizing the residual in some sense for various choices. How well does it do? With 3 points in finite difference, you will never get this accuracy. But these methods are very good. You can see n equal to 1, just one weighting function, just one coefficient. N equal to 2 means I have 2 basis functions, 2 unknowns to find out. N equal to 3, and this is the exact solution. And this is the solution evaluated at different independent values of x. Of course, 0, it satisfies the condition. We constructed the function in such a way that the boundary condition is satisfied. In this case, the initial condition that's satisfied. Okay? So you need to look at the error, 1.4 against 1.2214. That's pretty bad, right? So if you take the average error over the entire domain, that error is 0.28, almost 28%, you can say, right? But n equal to 2 brings it down tremendously. With 2 points, you are able to get 0.8% accuracy, if you like, okay, over the entire domain. With n equal to 3, it's really fantastic, 0.00046, okay? And that's why these global methods are, even though they involve a lot of work, you need only few terms. You get fairly accurate solutions. Now here I'm just saying you verify this. There is the least squares method, okay, with wk equals dr dak and n equal to 3. What you should get is that if you do it once, then you understand it completely. So I've given you many options, but pick one of them and go through the integration, okay, and see whether you get all the elements and see whether I have any errors in these matrices, right? So what you should get is this for A and B. Then you invert that and you can construct a solution. And if you have a subdomain method where my domains are 0 to 1/3, 1/3 to 2/3, and 2/3 to 1. So I've divided my domain into 3 subdomains, and I have again n equal to 3, so 3 coefficients. So once again I get a 3 by 3 matrix. Okay? But in all these cases, It's the same formalism, and you always get a full matrix. If you have 0, it's only by coincidence, not because of structural design of the method. Collocation method. What does the collocation method do? Takes the residual at those points, 0, 0.5, and 1, at the two ends and in the middle, okay? And evaluates the residual at those points and sets them equal to 0. So there is not even an integral for this one. Why? Why is that not an integral? In all other cases, you need to do an integration. But when you, in the collocation method, what do? You pick your weight function to be delta of xk minus x, something like this, right? So this delta function is 1 when x equal to xk is 0 everywhere. So what does that do to that particular equation? Do you know what happens to the integral of a function multiplied by a delta function? Do you remember it from your? So what I'm asking is, if I have some function f of x, okay, the function is like this, and I find the integral of f delta dx. Now delta is the delta function. So the delta function is just infinity at one point and 0 everywhere else, right? So when I integrate that, it just picks the value of the function at that point, okay? That's what happens. So you just have to take the residual and put in the residual variable x, you put x equal to 0 or x equal to 0.5 or x equal to 1. So you will get 3 equations from there. That's why we call it a collocation method. We are making the residual equal to 0 at those selected points. I guess I'm running out of time, isn't it? So this compares all the different methods. What are the coefficients? Let me just finish with this one. Just take a couple of minutes, okay? So Galerkin method will give you these coefficients, which we already saw. Okay, and that is the best method for n equal to 3. For a 3 by 3 system, that's it. And if you take a Taylor series, this is what you will get. Do you understand what I mean by Taylor series? E to the power x, expand it, take the first 3 terms. Okay? It will become a poorer and poorer solution as you go farther away from the reference point. Okay? Whereas these are trying to minimize in a global sense over the entire interval the residual, whereas Taylor series doesn't do that. So Taylor series would be the worst solution of these. Now here I have something called an optimal collocation. That is the one that uses the roots of the polynomial, orthogonal polynomial, as the basis function. So in this case we are using Legendre functions and their roots and evaluate that. And so you'll get these coefficients, but those roots are here. They are all tabulated. All these polynomials and their roots, all the properties are tabulated in the book. Also, a good source for this is the book by Finlayson, Nonlinear Methods in Chemical Engineering. And he was one of the pioneers who did a lot of work on orthogonal collocation in the 70s and 80s, I think. So it's a good book that documents all these things very well. And you find the root mean square error for various methods. This we already saw as the best method. Least squares is pretty close to that. Subdomain is not bad. Regular collocation is not as good, but optimal collocation combines, competes with the Galerkin method. Between Galerkin and orthogonal collocation, which one do you think will involve more work? Sorry. Galerkin and collocation, not orthogonal collocation. Between collocation and orthogonal, amount of work is not the same. The amount of work is the same, it's not different. Just evaluating the residual at certain points.
Yes.
And here, you are selecting the points intelligently, knowing what is the best location. The collocation method would be the easiest one. You don't have to evaluate any integral. Right? You just evaluate the residual at those locations. And the Taylor series is 0.02. Okay, spelling there. But trial functions are global in the domain. From 0 to 1 they are defined. The finite element method will define locally in each sub-region. And so the finite element method will have sparse matrices. Okay, because the functions are local, they don't influence cells far away. But here the matrices are always dense. And the Galerkin method is probably the most accurate of the method. So we'll see how to extend this to more complicated differential equations. And one of the key problems here is I get the solution in terms of the coefficients. So I need to put the coefficients back to evaluate the solution. So is there a way to get rid of these coefficients and get the solution in terms of nodal values, which is what we did in finite difference. We get the matrix in terms of unknowns at the nodal points. Here we don't do that. We get the coefficients, we need to put them back. And we'll see how to do that. And that will also be a key feature in finite polynomials we construct, or in terms of the unknown values at the nodal points.